Hello everyone. It is a pleasure to introduce our speaker, William Oregon from the University of British Columbia, Canada. The title of his talk is A Short Proof of a Sum Product Result.
Okay, thank you very much for the introduction. Happy Valentine's Day, everyone. The aim of the talk is to give a very elementary, proof of some form of some product result. And what that means usually is if you have some object, usually some set, or maybe a measure, and it has some suitable non-concentration properties, then if you consider some you view this set, you view that the sums of this set and the products of this set, or some combination of that, then you expect some sort of growth in some quantity, maybe cardinality or its dimension exponent or something like that. So I'll explain sort of what I mean by that in the coming talk. I should also say that this is joint work with Hong Wang and Pablo Schmerkin as well. So let's prove this theorem first. So this is sort of a baby theorem, and then we'll go on to a more general case later on. So what this theorem says is that if you have some S10 Frostman measure, S is bigger than a half, strictly bigger than a half, and that's quite important. Then, if you have A as the support and it's contained in the interval 0, 1, that's not so important. But what I claim is that if you consider some suitable this set under some image of some sums and products, like I have this expression here, then you have some sort of growth. So what does this say? This says that this support of this measure, well, when you push it forward under some addition and multiplication, then it has a positive Lebesgue measure. So essentially, the dimension of this measure is increasing from S to 1. And I've written here what I mean by a Frostman measure. So I've gone for 10 as this constant here. It's not very important. That's the point of the 10 is it's just not so important. Just a Frostman measure, just essentially that if you have a ball of radius r, the amount of measure that can be in that ball is at most r to the power of s. Okay, so let's give a proof of this result. It's quite simple. And this kind of idea is present in this Edgar Miller paper, where they prove that there are no Borel subrings of the reals. So this is the same sort of idea. You build up. You essentially want to take mu and you want to build it up somehow. So one way you can do this is by considering mu cross mu, and that will live in the plane. It will be 2s Frostman. So and that 2s is bigger than 1. So now we have a measure in the plane and its dimension is larger than 1. So what can you do here is you can apply Marstrand's projection theorem first, and that shows that when you for a typical projection to a line, then this dimension is preserved, let's say. So because the dimension of 2s is bigger than 1, actually you can't have dimension 2s on the line. So it says that it has dimension 1 essentially, or it has this positive Lebesgue measure. So that's one thing you can do. And remember, we're trying to start from A and we're trying to build it up to something something involving sums and products. Well, this is sort of some sort of start. Okay, we don't really know what V is, but V is so this holds for basically every V. And you can also use the Masterton slicing theorem as in tandem with this. And what does that say is like, okay, you find this projection where it preserves the dimension. So on this line here, this span, I'll try and get rid of this somehow. So on this span of 1 and V, or this line here, so it has positive Lebesgue measure, but because the dimension of the original set is more than 1, there has to be some sort of leftover along this slice. And actually, the slicing theorem says that sort of for typical slices of the pre-image of this map, then this has essentially a dimension 2s minus 1. So, and a weaker conclusion you can draw from that is you have to be able to find 2 points on a slice that they're quite well separated and they map to the same place. So that's what I've said here. I've said you can find A, B, C, D. Okay, we only need that C and D are separated, but they map to the same place under this map. Well, that now gives you a formula for V in terms of elements from A. So that's good. So let's use that. So from the first part and the fact that this is separated, you can multiply these by C minus D. Well, that's not going to affect the Lebesgue measure because you're not contracting your set particularly, so that's fine. And then from the second part, you have this formula for V C minus D. Well, that's good. And then you can just plug it back in, and you get this result that is what I claimed. So you have this sum product result. It works for Frostman measures when the dimension exponent S is bigger than half. So that's good, and that's a very simple proof. It uses only Marstrand and Marston slicing, which is essentially bread and butter now. Okay, so we have some sort of sum product result going, and this idea is, but as I said, this idea was present in the Edgar Miller paper, where they proved that there are no Borel subrings of the reals. And this is sort of another way of expressing that, isn't it? You've got some measure that could represent some sort of set in the reals. You know, you have a set of dimension S, house of dimension S, you put a S Frostman measure on it. Well, if it was a subring, you wouldn't really expect a conclusion like this at all. You'd expect to have closure under, you know, your ring operations. So this is another way of sort of saying that what they concluded in their paper. Okay, so this is good. This works for S bigger than a half of what about other values of S? Does this strategy work just like this? And the answer is no, unfortunately. It's a little, yeah, it doesn't quite work. So we'll see why it doesn't work later on. But let's go for a new theorem here. So if let's consider a half n Frostman measure, and I've rather foolishly completely left out a conclusion there. But all I want to say is that if you start with you start with A and then you beef it up using sums, products, and addition, it's not going to be anything like this, but you can beef it up. But let's just try this. Let's just try the same. Let's just try the same strategy when S is a half. Okay, so the rest of the talk essentially want to talk about this case when S is a half and see what we can do. So let's just try the same strategy immediately. So you can just do the same thing, really. You can do mu cross mu cross mu, and that lives in R3, and that's 3/2 Fossman. Okay, this constant's not particularly so important. And then you can apply Marstrand and the slicing theorem again. And what you can find, I mean, this sort of thing is, I can get rid of that. We can find this U and V here. So this is going to represent our projection. And then we can find a sextuple in A with okay, E minus F is separated, so that first of all, this is sort of projecting to now the line sort of spanned by 1 U and V. Wish this would stop popping up. This is this is a projection of A cubed to the span of 1 U and V. So this is just by Marstrand. This is positive Lebesgue measure, quite big Lebesgue measure. So Lebesgue measure is about 1. So that's good. Again, we've got some sort of sums and products of A. Okay, it's in relation to this U and V we don't really know about yet, but we can try and go for a similar strategy as before. And then, okay, I'm very bad at drawing. I mean, I'm not particularly good mathematician, but at least I know that, I at least made the correct decision of mathematics over fine art, as you can probably tell from this drawing. And I've tried to do the same drawing I did before here to essentially represent that we're projecting to this line here. And then you've got these 2 points in A cubed, which are separated, and they're projecting to the same point. And then I've tried to draw this slice, and I've done a very, very bad job of it. This drawing is absolutely not my forte, but the points of these points lie on this sort of on this planar slice. Okay, but I'm really just trying to illustrate that we have this strong non-injectivity that we had before. Okay, so let's just try the same strategy. We now have some relation between U and V and elements of A. That's good. Okay, so let's just go for a very similar strategy to before. So actually, I can rearrange this equation too, and you can write it. You can have this V E minus F in terms of U and then some elements of A. So that seems quite good. It looks like we can remove essentially V and write V in terms of U and A. That's better than having 2 elements we don't know. It seems to be now 1 element we don't know. So then, okay, we can similar to before, we now sort of substitute in, we multiply through by E minus F, and then we substitute in this equation up here. And we get some sort of something a bit like this. Okay, we have this, if you remember this from before, this A minus A multiplied by A plus A minus A multiplied by A. So we have we have this sort of we have something involving lots of sums, subtractions, and products of A, but with U. So it's a bit like we've got back to the problem before, haven't we? So if we set B to be this thing here, then we have this conclusion. So it's back to the first problem that we had that I showed you that was quite straightforward. So yeah, so let's just pause there for a second and just think about what we've done. Well, we start with something like this from Marstrand. I do wish this would stop happening. Start something like the Bohr equation 1 from Marstrand, and then the slicing like before, allows us to eliminate the variable v, and then we have some sort of we can be considering the Lebesgue measure of something involving just sort of A under its ring operations and U. So that's good. And remember, that's where we were in the first result that I showed you here. So the thing you would like to do next is essentially try and do the same thing we did before, which want to apply mass strand and mass strand slicing. Well, we've already got mass strand. But the issue is now is that we don't have any slicing theorem anymore. So A had dimension 1/2. I mean, you might like to expect that B would sort of have a dimensional exponent bigger than 1/2, but that's sort of what we're trying to prove. So we can't really assume anything there at all. So we're sort of back to, well, we've got this B here, but we don't really know. We know this. We don't have any slicing. I mean, the slicing needs that you have that B cross B would have dimension bigger than 1 to allow you to have some left over on the slices, but we don't have that. Okay, so we need to do something else. So I've sort of written here that there's no guarantee. If you call this map pi, and this map pi is the projection to the line spanned by 1u, there's no guarantee that this satisfies this non-injectivity that we had before. So what do we do? We have to do something vaguely. We have to try. We can't rely on that. So we have to try and do something else. So I'm going to claim that, okay, if we're willing to replace B, if we're willing to beef up B further with ring operations, which is fine, because remember, that's what we're trying. We're trying to say that if we have an A, we start with A, we beef it up with ring operations. We want to claim that grows. Well, that's fine. I'm going to claim that if we can do this to B, then we can actually guarantee this sort of strong non-injectivity. So, okay, how do we do that? So now I'm going to pick. Okay, I'm going to pick lambda, the lambda for length, let's say, and that's going to be the Lebesgue measure of B cross B plus UB. And the lambda is sort of basically 1. So I'm sort of, this might be, I don't know, 1 over a million, but that's in my world and many people's world, that's essentially equal to 1, isn't it? And then for exposition, I'm just going to suppose that 0 and 1 are in A. This isn't a terrible thing to suppose, because you know that A is a support of this Frostman measure, and this measure is very non-concentrated. So actually, the support, the convex hull of the support of this measure is essentially an interval of length 1. It's about length 1. So let's just suppose for ease that 0 and 1 are in A. There's no need to, it just makes things a little nicer. And now I'm going to draw this picture of, and try and explain how I force this non-injectivity now. So let's suppose we're projecting B cross B over here to this line. And I've drawn this sort of big tube that's, this tube is, I don't know, you can say that it's maybe, let's suppose that the convex hull of B plus UB is contained in an interval of length, I don't know, well, at most say 2 or something. You could choose a tube of width 10. or even larger if you like, but as long as it's something not too ridiculous. And then we don't know we have this nice non-injectivity property about B cross B. So what I'm going to do is I'm just going to say, well, I'm going to pick up B cross B, and I'm just going to pick it up, and I'm going to place it upwards, sort of away from this line. And you can just keep doing that, and by translations. And the translations I'm going to use are just these natural numbers, or these n1, n1 prime. I'm sure you probably believe me that you could do this. You could probably take n1 to be 5 or something, and I want these copies to be very well separated. So you could take them, I don't know, 5, 5, I don't know, 10, 10 or something like this, but you probably, don't want to get into too specific details here, but there's a way to do this. And remember, I suppose that 1 was in A, so actually this n1, this is in A plus A plus A plus A plus A plus A plus A, n1 times, and so on. So that's that's okay. We've sort of beefed up B cross B with this new thing here. And well, yeah, now you have some sort of, it looks like you have some sort of non-separation going on here. So let's keep doing this. Let's do this capital M times. And then yeah, let's see if this works. So if you still don't have them, the idea is that we'll end up, if you keep placing enough of these, if you still don't have this non-injectivity, then the measure of all of these projections will exceed the width of this tube. So eventually this sort of process has to stop. So as long as you if you still don't have this non-injectivity after placing more than the width of the tube divided by the Lebesgue measure of B plus UB, and then what will happen is that if you now consider B prime, which is this union of all of these sort of translated copies of B cross B, well, this projection is the projection to x plus uy. Well, this is going to exceed the width, so that just can't happen. So as long as you have L large enough, this B prime is contained in B plus some number of sums of A, and again some number of sums of A. L is some fairly large number. So I never made any sort of claim that this proof would be a very this theorem would give a particularly good quantitative bounds on this, but I'm just claiming that you do get some kind of sum product result, even if it's very poorly quantitative. So now if you set C to be this thing here, B plus A plus A plus A plus A L times, then we're in this situation here. We have this C. So, and then we do have this non-injectivity that we had before, because you have all of this, you must have some sort of non-injectivity if you place enough of them, just by the pigeonhole principle. And then you can just take two which are separate here. So you're assuming there's no special non-injectivity here. And so there must be some between some of these translated copies, and that's obviously very well separated. And then you can just go as before. And I showed you how to do this in the first theorem. So in the end, you get some very if you consider enough ring operations of A. So I'm not in the preprint that we have. We didn't bother to really write down what you get to at the end it's some very long polynomial expression. But as long as you're willing to do that, so if you do the next step, you'll replace C by C minus C times C minus, I think, plus C minus C, something like this. So in the end, you'll get some very long polynomial expression for A, and this will have Lebesgue measure about 1. Okay, so yeah, I'll stop there.
Any question?
Hello, Andreas.
Hello, how are you doing?
I'm okay. How are you?
Yeah, everything's good. Good to
Good.
see you.
No, suit you.
No question, right? Okay. If not, let us thank the speaker again.